In your packet on section 3, we're going to do some focus on friction. Friction is a force that acts on a material that's in contact with one another. So a friction is due to roughness of the two materials' surfaces. It depends on both kinds of materials and how hard they're pressed together. So we're talking fridge and kitchen floor, or fridge and rug. And fridge full of food, lots of pressing force, or empty fridge. Friction is always in the opposite direction of relative motion. So you take how those surfaces rub and resist that motion. Air resistance is the word that we use to describe friction when it's due to air. Friction is going to be F subscript F. Sometimes you'll see it as a curly F as well. The direction of force of friction always opposes the motion. So here you have a crate, and as you push it forward, the rubbing between the two surfaces will have the friction pointing left. Because the crate is sliding to the right, the friction on the crate will be to the left. When it comes to air friction, just the way it's moving in the air, so this is moving down with the velocity, so the friction force from the air, or air resistance, would be up. If something is thrown up like a tennis ball, in that case, then the air friction would be down and mg would be down. And that's totally possible too. So there are times when friction will go with the motion. So I'd like you to take your hand and put an object on top of it. And then you will accelerate your hand, object. And then you'll accelerate that system to the right. And we'll take a look at what's happening. My hand with my object on it. As I move my hand, as I accelerate my hand to the right, then what is it that keeps the teapot on my hand? Well, it's the friction force, FF, from the palm of my hand. So on the teapot, the friction force is actually acting in the direction of the motion. Wait, but I thought you said friction force always opposes the direction of motion. What? Let me clarify what I mean by that. The friction force is opposing the potential slip between the palm and my teapot, and the teapot would slip left. Let me show you again. Friction force to the right, accelerating the teapot. Friction force to the left, slowing down, deaccelerating the teapot left. Both of these FFs oppose the potential slip. So here you saw the tissue box actually slip out from underneath the teapot because it doesn't have as much friction as my palms. The teapot is rubbing against the tissue box, creating a backwards friction force that I have to pull against. And on the teapot, there is a forward friction force, FF, but it's just not enough to make the teapot's acceleration match that of the tissue boxes. Getting ourselves out of the tea world, let's go back and just reiterate some of the things that friction will depend on. So friction depends on the type of material. My palm, rougher, tissue box, smoother. Then how they're pressed together. So let's explore this just a little bit more. Check it out. We have some friction on our system. We're going to let our man push a single crate. Notice the friction force will match his pushing force until a certain time when he can get the crate moving. 150 newtons of force. It's a force he needs to get the cart moving. Double the amount of crates. Then the man's going to start pushing, and you'll notice that 150 newtons just doesn't do it like it did before. So he's going to have to push even more, 200 newtons. No, still more, 250 newtons, still more. Wow, at 300 newtons, he's finally getting the system moving. So the amount of friction force must depend on the mass. Great, so that simulation let us see how much force being pressed together affects the amount of friction force. How much force is going to be this reflection of the normal force, the force that comes between an object and a surface. This is often equal to mg, but is not always. For example, if you take an object and pin it up against a wall, you might push it, Fp, into a wall. The wall will push back against it with equal and opposite forces. So Fn is this amount of how much force we're pushing with. In our simulation, it was just equal to the mg of the different crates. Let's look at the next part of our friction force expression. So mu, this coefficient of friction, refers to rough versus smooth. Let's look at that in some detail. Look at the ground between the plate as we change our friction. As we bring our friction down to none, it produces an ice-wood combo. As you increase our friction a little bit, it's now wood-wood combo. Increase the friction more. Do you notice the prickly bits of like grass or rug or something that are being created underneath our crate? And as we string it all the way to lots, then you can see the number of those kind of fibrous pieces increase. This is what mu stands for. High mu, very sticky surfaces, lots of interaction. Low mu, ice. A Google search for this mu, coefficient of friction, reveals tables like this, where they list two materials that will rub on one another, and these two different mu values. Mu s is for static/stationary, while mu k is for kinetic. You can look at these and realize that they are all under the value 1, and mu k is less than the mu s. So the way to have a mu above 1 is through some interaction that is no longer just frictional force, like glue or some sort of other adhesive, like Velcro. The last dependent factors on this list are whether you are moving or not. If you are not moving, we're going to use a static friction coefficient, mu subscript s, like you saw in the chart. If you are moving, things will be a little bit easier to keep going. We're going to use more of a mu k. From our chart, you saw that the force of static friction is typically more than the force of kinetic friction. Let's take a look at that in a simulation. Simulation, they're going to show us the forces on this object. We're going to have the weight down, which you can calculate because they give you the mass here, and then the normal force. Additionally, we're going to have some friction that we can make, static and kinetic. The word static, remember, means stationary, and kinetic means moving. What we're going to do is we're going to pull on this string harder and harder and harder to see if we can get the block to move. So you pull a little bit. Now notice, as you begin to pull, the static frictional force will match the pull. And you pull harder, and you pull harder, and yet there's still no motion. I'm sure that you've experienced this, maybe trying to pull a couch on a carpet, right? You push, and yet it's still not going. Keep pushing, and then, finally you get it to go. And that resistance force against you is not as large as the one that was there previously. Now you can pull harder if you want, and notice that doesn't affect the resulting friction on the other side. Flipping to some problems, you'll find the chance to use your free body diagrams, concept of weight and normal force, and the friction force is mu times normal equation. So go ahead, try 1 and 2. You'll check them out later in the video. But let's check 3. Something interesting is going on in 3. It wants to know a 1.5 kilogram mass is pulled at a constant speed with a force of 6. What's the mu? So here we have an object and it's being pulled along a surface with a constant speed. You're pulling it with a force of 6 newtons. Well, constant speed. What acceleration does an object with constant speed have? 0. So then how much friction force acts against that object? Well, if the sum of the forces equals ma, and a is 0, then our two forces, F pull and FF, must be balanced. So when we think about FF, we must deduce that it is also 6. Now you might look at a picture and see 6 left and 6 right and wonder how it is that it's moving. Let me show you. We're going to let our man push a single crate. Notice the friction force will match his pushing force until a certain time when he can get the crate moving. 150 newtons of force. It's a force he needs to get the cart moving. Now that he's got the cart moving, he can drop his force back down to be 100, in which it matches the frictional force. And he's able to continue the cart moving with constant velocity. Okay, so now you saw that as long as you get it going, balanced forces can have you moving at a constant speed. That speed could be 0, but let's keep moving. So once we decided that our friction force is equal to 6, we can say FF is mu times the normal equals mu times the normal. Let's take a moment to figure out what the normal is. mg is 1.5 times 9.8. 14.7 newtons. So the normal force is referring to how much the surface must push back. Well, the object's not accelerating up and down, so the normal force is also 14.7 newtons. You'll find that most of these times these things are equal, unless in an elevator. Here we can solve for mu. It comes out to be 0.4. Let's try some practice problems together. For every problem, we're going to start by drawing a free body diagram. We will need to know that the weight down will be mg. The next thing that we're going to do is we're going to sum the forces. If we need to, set them equal to ma. We might not need that step, in which case we can go right to friction force equals mu times the normal force. Okay, here's our plan. Let's go. So here you'll have an mg for our physics book down of 0.5 times 9.8. There's a surface below our physics book that will push up on it with a normal force. The normal force will also just be equal to mg because it's not accelerating up and down. The book's not flying off the table. So that's 4.9. Fn will equal mg. Just to write it down for you there. Okay, so that's our sum of forces equals ma. Now let's go on to ff is mu times the normal. So we will take friction force, ff, and we will set it equal to mu, the coefficient of friction between the book and the table, times the normal force, which is 4.9. That will allow us to calculate our friction force, which is 0.98 newtons. We can put that, so if our book is sliding this way, velocity, then our friction force is against it at 0.98 newtons. Do be aware that while friction force is a force, velocity is just a direction of motion. Go ahead and try some of the other ones and check your answers as needed. Looking at this next one, it says what mass is being pulled along the surface if the coefficient of friction is 0.35 between the mass and the surface, and it causes 20 newtons of force. I think it's supposed to say just newtons, friction force. Okay, so we have some mg down. Now the normal force from the surface up will be equal to mg down because you're not in an elevator or pulling on it in any strange way. Then we'll have our friction force to the left. ff is 20 newtons. Okay, so that's step 1, free body diagram. Step 2, mg. We can't calculate mg here, but we can say that it's m times 9.8. Step 3, sum of the forces equals ma. Well, we don't really have an a or anything like that. We already applied that up here, so that's good to go. Now, last step, friction force is mu times the normal force. Okay, so 20 equals 0.35 mu, the coefficient of friction, times the normal. The normal is mg, and let's fill in g as 9.8. We'll solve for m now. I get 5.8 kilograms.